In this chapter, we'll talk about two concepts. One is related to temperature and other is the heat. Okay. So heat and temperature are basically different concepts. Okay. We'll talk about these things. And we also measure heat and we also measure the temperature in different scale. Okay. So we also talk about how heat transfer happens from high temperature to the temperature, lower temperature, and different mode, how heat will be transferred. Okay. So thermometer is device to measure the temperature. So thermometer uses different physical property of different substances. For example, in some kind of thermometers, they take the property of volume expansion of liquid, volume expansion properties. In some thermometers, we can also consider the the change in the change in electrical properties with temperature. So different kind of thermometers could take different kind of physical property of substance. So for example, the thermometer we are using in our daily life in general, this uses the volume expansion of the liquid, this kind of properties. And these days you have seen that we can also use the thermometer which is based on in the infrared thermometers. Okay, so different kind of properties, substance properties can be used to build the thermometers. So in this picture they give you basically three examples. One is based on the thermometers based on the volume expansion of liquid. In second, they consider the liquid crystals square, which actually changes color with the temperature. And in the third example, we consider about the infrared thermometers. Okay, so these are the physical properties of different substance that change with temperature. So let's talk about the temperature scale. In general, we use we use generally Fahrenheit scale, Celsius scale, and the Kelvin scale to record the temperatures. Okay, so in general, to give the relation between these three, we consider two standard points. One is the freezing point of water, and other is the boiling point of water. Okay, so the freezing point of water is considered as 0 degree, same as 32 Fahrenheit and 273.15 Kelvin scale. They are the same in different scale. Okay. Similarly, boiling point of water is 100 degrees Celsius, 212 Fahrenheit, and 373.15 Kelvin. So these two are the two standard points based on which we can find the relation between the temperature scales. Okay, so let's start with these 2 points. So we just saw that these are the scale. For example, we say the body temperature is nearly 37 degrees Celsius in Celsius scale, and it is 98.6 for the Fahrenheit scale and 310.15 in the Kelvin scale. So they represent the same temperature in different scale. So let's find the relation between these. Say for example, say I'm drawing the same scale over here. So this is my scale. Lower temperature is lower scale is it is the 0 degree, up is 100 degrees Celsius, and in Fahrenheit scale we just know that it is 32 Fahrenheit, and it is 212 Fahrenheit, and in Kelvin scale, it is 373 Kelvin, and it is 273 Kelvin. Okay, so we know that this all represents the same temperature, and this all represents the same temperature. Okay, so for example, we want to find the relation if at a particular time a substance has temperature C. We want to know what is the temperature in Fahrenheit, and we want to know what is the corresponding temperature in Kelvin scale. Okay, so you see, between in Kelvin scale, uh, it's the sorry in Kelvin scale, the freezing point of pure water is 0 degree, and boiling point 100 degrees Celsius. So it is equally divided into 100 parts. Okay, so it is in Kelvin scale, we can see it is 100 equal parts. We divide it between 0 and 100 like this. Okay, 100 equal parts. You can see in Fahrenheit scale, these 32 degree Fahrenheit and 212 Fahrenheit is equally divided into 180 equal parts. So 1, 2, 3 like this. So total is 180. Okay. In Kelvin scale, again, it is equally divided into 100 equal parts like this. Okay, so if you want to find the relation between these, so you can write C minus the lower temperature, lower point, it is 0, over divisions is 100. This should be equal to F, we want to find that temperature, minus 32. 32 is the lower. We just considering, we are considering as a lower level and higher level, and it is equally divided into 180 parts. And in Kelvin scale, K minus 273 over 100. Okay, so we can simplify a little bit. It is C over 100, and it will be equals to F minus 32 over 180, and equal to K minus 273 over 100. This is actual relation between, this gives the relation between Celsius scale, Fahrenheit scale, and Kelvin scale temperature. Okay, so we can go over this to get some relations. Okay, so let's see here. Okay, so let's take only out of, just take the Celsius and Kelvin scale. So we can write, say for example, C over 100 equals F minus 32 over 180 equals K over 273 over 100. So we can cancel. So if we take just two these, so we can cancel 0, 0, and 0. So we are left with 18. Let's say C over 10 equals F minus 32 over 18 equals K minus 273 over 10. Okay, if I take just these two, what will happen? Let's see, it will be C over 10 F minus 32 over 18. Then we can simplify like this: 18C over 10. Okay, then equals F minus 32. Then I can find the relation F as 9C over 5 plus 32. So we can convert from Celsius to Fahrenheit scale. Okay, if I take this first one and this one, last one, then you can write C over 100 equals C over 100 equals K over 273 over 100. Then this 100 cancel out, so basically C equals K 273. Then you can write C plus 273 equals Kelvin. So we can convert from Kelvin to Celsius scale, or we can write equivalently in a more accurate form. It is 273.15 equals Kelvin scale. Okay, so these two equations will give you the conversion from one scale to the other scale. Okay, so you can try these questions, like they give you the temperature in Celsius scale is 25 degrees Celsius. Then you can use the equations that just you saw in the Fahrenheit scale in the Kelvin scale. Okay, so next, it is called the zeroth law in here. So zeroth law is basically telling you that if two systems are in equilibrium with the third systems, then they are also mutually in equilibrium. Okay, so let's see what actually this law is telling. Okay, so this law basically defines thermal equilibrium. So by the way, what is my thermal equilibrium? Then thermal equilibrium basically telling that no change in temperature. That tells you that no net heat flow. Okay. So for example, it's saying that, say we have two objects, object A and C. We have, say, object C in equilibrium. Okay, so they are in equilibrium. Means there is no change in temperature, means A and C has same temperature. Okay, so we are saying here A is in equilibrium with C. Okay, And this B, we have the other object B, is also in equilibrium with C. So B is in equilibrium with C. Then according to this law, what is telling that if this is the condition, then this A and B is also in equilibrium. So this means A and B are also in equilibrium. So here we are talking about the thermal equilibrium. Thermal equilibrium. Temperature remains the same to all of these. Okay, so this actually defines the thermal equilibrium. So in short, we'll come this point later, but we'll see what is difference between heat and temperature. So heat and temperature, I told you, is different. One version is this: heat is a form of energy. So it is measured in joule. So joule is the unit. Okay. The temperature is not a form of energy. So it measures basically how hot or how cold an object is. Okay, so it is measured in basically in, you saw, in Celsius, degree Celsius, or it could be in Fahrenheit, or it could be in Kelvin scale. So many. So just like joule, energy can be also measured in calorie. We'll come to this point later. Okay, so say for example, we have a spoon. Okay, so it with water of 100 degrees Celsius, a spoon. Okay, water, a spoon. So this is the spoon. Okay, we have a beaker of water. So say its temperature is lower, is 25 degrees Celsius. Okay, so you can guess, say it has only, we're assuming for shortcut to make easier, say it has only 100 atoms of water. Could be it has 10,000 atoms of water. Okay, so if you consider the energy, so total kinetic energy is proportional to temp heat. So if you consider heat content, this beaker with water will have more heat content as compared to the water in the spoon. Okay, so average, if you consider average kinetic energy, which is proportional to temperature. So heat and temperature are different things. So we'll come to this point later also. Okay, so thermal equilibrium will tells you whether two objects or two substances are at same temperature or not. If they are equilibrium, there is no net heat flow. But if they are not in equilibrium, there must be net heat flow. Okay, so we just talk about the absolute zero. So absolute zero is basically in Kelvin scale, it is negative 273.15 degrees Celsius. The importance of Kelvin scale is that at that temperature, the motion of all molecules would cease. Means there will be no molecules in motion. All will be basically at rest. Okay. So we can see in terms of the graph, this is the, along the y-axis, we have pressure. Along the x-axis, we have the temperature in the Celsius scale. So the experimental fact is this: if you take in any number of ideal gases, And if we plot pressure versus temperature graph, we'll see that they all meet at this particular temperature, minus 273.15 degrees Celsius. This means at that particular temperature, you see that pressure is zero. Okay. So this temperature where pressure, the absolute pressure of any gas becomes zero. So this is the temperature at which this happens is called the absolute zero temperature. Let's talk about the thermal expansion now. Okay, so thermal expansion means if you hit any object, it will change in length. Say for example, we have a rod. It has a length, say L naught. Okay, at temperature T naught. Now we hit that substance, say, then its length will increase. For example, now length is this. Say, now length will change. So now this new length will be L naught plus change in length. Okay, we have a small change in length, delta L. So let's write here, L naught is the initial length. Okay, T naught is the initial temperature. Okay, so you see L, and then you see here L naught plus delta L is the final length. Okay, so you can see if length increases at that time, we must have supplied the heat. So final temperature will be, so we'll say T naught plus delta T. This is the final temperature of the rod. Okay, so we define here linear expansivity. So we define here linear expansivity. We generally represent by symbol alpha. Okay, or is also called coefficient of linear expansion. Coefficient of linear expansion. So we define this as alpha is change in length over initial length times change in temperature. Okay, so you can see here the unit of alpha is, you see here, is per degree Celsius, or it could be per Kelvin, depending on in which system we are measuring the length. Okay, same thing will be true if you consider the area. Okay, so in term of area, say this is in term of length. If you consider in area, say it has initially, this is initial area. If you heat, this area will increase. So this is initial area. Then this will be, say, final area. Okay, so this means we can similarly define 2 alpha equals change in area over initial area, so initial area times change in temperature. Okay, so in this case, we'll see that A naught is the initial area, And you see delta A is the change in area. Okay, and you see delta T is the change in temperature. Okay, so the key point is that different substances have different alpha value. So copper will have different, steel will have different. So different substance will have the different alpha value. Okay. So next we define the volume expansion. Not only length, not only area, there is also volume expansion. So volume expansion, you know, is obvious, is possible for solid, it is possible for liquid and gas. But you know that linear expansion and surface expansion is possible for only for solid only. So we defined coefficient of volume expansion again. Coefficient of volume expansion, or we also call it volume expansivity. Okay. So we represent basically by symbol beta. So this will be change in volume over initial volume over change in temperature. Okay. So here we started on some object. Say we have this bigger object. Say it has volume V naught. So this substance has volume V naught. So when you heat, it will become bigger. Okay, so its volume may be V naught plus delta V. So here initial volume is V naught. Final volume equals V naught plus delta V. Okay. Initial temperature equals T naught, and final temperature, okay, final temperature will be T naught plus delta T. So based on that, we can define the volume expansion. So it is clear that the unit of beta is also for degree Celsius or for Kelvin. It does not matter which system, which temperature measurement scale we'll choose. So it's also, beta is also different for different substances. Okay, it will not be the same for solids only. Only we can define, alpha and 2 alpha. Okay. So, but this is true for all solid liquid gas. So beta equals 3 alpha. Okay. So this is the relation we can apply for to find the relation between alpha and beta. Okay. If you have understand up to this point, you can answer these questions. Okay. So basically in these questions, we want to find how much taller does the Eiffel Tower becomes at the end of the day when temperature has increased. Okay, you can try this. These are the examples. So these are the effect. We need thermal expansion. We have the effect of thermal expansion. That's why you see a gap is left in the bridges where the expansion happens. For example, in this, if this is a metal strip at temperature T naught, after heating, so this is the case of after heating, it bends because these two strip has these are different materials. This is different materials. This one is the different materials. This one is the different materials. So they are different materials. So they expand differently. That's how they get curved. Just as the volume expansion, if you have a hole, the hole also behaves as a substance. So hole is also gets bigger and bigger with increasing temperature. This means if you have a smaller hole, if you heat it, it will not shrink, it will expand. Okay, so let's see what is thermal expansion is going to give the stress. So for example, we have learned before that Young's modulus of elasticity is stress over strain. That's how we define Young's modulus of elasticity. Okay. So if you remember, for a series, so stress is force per unit area. This is change in length over initial length. So the F is the force applied. Is the area. So for example, if you have this wire, you are applying the force downward. So this is the area, cross-section area A. If you are going to change the length, so what will happen? Your initial length is this. After elongation, its length will go up like this. So this will represent change in length. Okay, so this represents delta L is the change in length, and L is the initial or original length. So you can write force per unit area in terms of the Young's modulus. So you can write F over A equals Young's modulus times change in length over initial length. Okay. But if you remember, we also know that alpha is change in length over initial length times change in temperature. So this means we can write change in length over initial length equals, this will be equal to alpha times change in temperature. Okay, so we can combine these two results. If you combine these two, okay, so we are getting F over A equals Young's modulus times alpha times change in temperature. Okay, so this means because of heating, the object could expand. It would, if it expand, it will exert the force on the other object. Okay, so we can use this equation. Based on that equation, you can solve this problem. Okay, so they give you everything you need to plug in, and you can find how much stress it will exert. Okay, so one of the important concepts we're talking about is the expansion of water. So in general, let's talk in general. What will happen is this: if you expand, if you heat, an object will expand. Expand means, say for example, volume increases. If you heating the liquid, okay? But water has different kind of properties. Say, let's start with the graph. You see that water has highest density. So highest density at 4 degrees Celsius. This tells you highest density means what? Density means mass per unit volume. So mass will not change. So if this is maximum, then this will be minimum. Okay? So at this temperature, lowest possible volume. Okay, so the graph shows you that if you increase the temperature or if you decrease the temperature, volume increases. Okay, on both sides, if you go either side, intensity decreases. If you go this side also, density decreases. What do you mean by density decreases? Means volume increases. It's also volume increases. See the difference here. If you cool, also volume decreases. If you increase the heat, it also volume increases. Okay, so this means the water has different kind of property than in general other kind of liquids. So this means water, if you take water at 4 degrees Celsius, means volume lowest. Okay. If you heat, what will happen? Say for example, it goes to this much temperature, 10 degrees Celsius, means volume increases. Okay, but if you cool, if you go to this side, say you are going to water still, but it at Celsius is temperature 0 degree, also volume increases. This is not in general happens. In general, if you heat, volume increase. If you cool, volume will decrease. Okay, so this kind of behavior, water is showing differently, is called a anomalous behavior of water or the expansion. So this is a very important concept. Because of that, all like fish kind of thing can going to survive survive even if the lake or pond is going to frozen. So for example, if this is a pond, so this is ice formation happens. This may be ice. So below still water, so it could be 4 degrees Celsius water. That's why all the fishes, all the aquatic animals were going to survive. Means ice could not be formed throughout the all pond. Okay, so let's stop here.